So far this week, we've motivated the need for an instantaneous rate of change as opposed to an average rate of change, and this led us to thinking about the idea of a limit. When we started thinking about limits, we needed to figure out a way to calculate or determine what a limit is mathematically. Now that we've had a bit of a brief overview of limits, we can move on to actually figuring out instantaneous rates of change, and that brings us to the mathematical concept of the derivative. Formally, or mathematically, we define the derivative of a function y equal to f of x in this way here. Now, it's quite messy, but don't worry about that. First of all, we've got two different ways of writing the derivative. The first one here, dy dx, and the second, f dash of x, mean pretty much the same thing if y is equal to f of x. So they're just different ways of writing the derivative of the function. The actual definition is over here on the right hand side, where we've got a limit as h approaches 0. On the top we have the function value at x plus h, take away the function value at x, and then divided by h. I've just put in a little plot to help us figure out what this all means. But basically, what we're doing is looking at successive approximations of delta y over delta x as delta x gets smaller. Or in other words, a change in x gets smaller. And here we've used h to represent that. So on the figure that I've drawn, what you can see there is a function, f of x, and a point here, the red point, where I want to figure out the slope of the tangent line to that curve. Well, if we put in another point up here, and join those with a line, that line itself has a slope which is approximately equal to the slope of the tangent line, but it's actually a fair way off. But what about if we moved that point further closer towards the red dot? In other words, decreasing the distance between the two dots in terms of their x-coordinates, or if you like, moving h towards 0, the difference between the two on the x-axis. Well, if we do that, we get something like this. You can notice that the line now has a shallower slope, and it's probably a little bit closer to the slope of the tangent line to the curve at the red dot. This time we've got a much closer distance between the x-coordinates of those 2 points. If you kept getting closer and closer, you're approximately or approaching the slope of that red line, the tangent line to the curve at the point. And this is basically what this here, limit as h approaches 0, the difference between the 2 points x values, of the function value difference over the x value difference means. When we have an actual function, f of x, and we try to find its derivative using this definition, we call that finding the derivative from definition, or from first principles. Let's have a go at an example right now. We have to find f dash of x, remember that's the derivative of f of x, for f of x equals 2x squared plus 3x from first principles, or in other words, using that definition. Well, the first thing we'll need, of course, is the definition of the derivative. And there that is. Now we don't know what h is. We don't have to worry about that until we actually do the limit. We do know what f of x is, so we can replace f of x with 2x squared plus 3x. Similarly, we can replace f of x plus h with the same function, but with all of its x's replaced by x plus h's. So that gives us something roughly like this. We leave the limit alone. F of x plus h is going to be 2 times x plus h all squared plus 3 times x plus h. I'm going to get rid of that line to give us much more room. Then I'm going to have take away f of x, which is going to be take away 2x squared and take away 3x. Remember that the minus will get taken through that whole thing. And that's all over h. The next thing to do is to expand all those brackets out and see if we can get any simplifications happening. Expanding the brackets gives us something like this, and then what we do is go through and look for similar terms that we can cancel out. The first thing is you've got a 2x squared and a minus 2x squared, so those are going to cancel each other. Similarly, there's a 3x and a minus 3x. All of the rest of the terms are different, so we can't get any more cancelling. However, when we go to the next line, note that all of the remaining terms on the top have h's in them, so we have a common factor, and we can pull that out. So we've got h outside of 4x plus 2h plus 3 all divided by h. And of course we can cancel those, common factor top and bottom. So the h's go away. Just copy that down to the next slide so we don't miss where we're at. And we can rewrite as the limit as h goes to 0 of 4x plus 2h plus 3. And notice we've lost the bottom of the fraction now, so it's all nice. The limit of 4x as h goes to 0, there's no h in there, so that actually doesn't make any difference to 4x, so we just leave it as 4x. As h goes to 0, 2h also goes to 0, so that's lost. And finally, as h goes to 0, 3 doesn't change either, so we've got 4x plus 3. Now that all the h's have gone, we've reached our result that the derivative of f with respect to x, or dy dx if you like, is equal to 4x plus 3. So that's our derivative, or our instantaneous rate of change for any x value of the function 2x squared plus 3x, found from first principles. The problem with that is, it was quite a lengthy process, and from experience I can tell you this is quite a simple function to differentiate. Things get much harder than that, so the working to figure out a derivative from first principles, or using the definition, gets much more complicated, and can take many pages. So, what we've been able to do is define some rules. People have looked at general functions and come up with some rules that you can use all the time to save you all that work of going through the definition of the derivative. And here's a few of those on this slide. And they just basically give us the derivative of a function of any particular type. Some of the simplest ones tell us that the derivative of a constant, that's just some number, is always 0, no matter what the constant is, because constants don't change, so that makes sense. The instantaneous rate of change is 0. Powers of a variable, like x to the n, those differentiate to give us that n number times x to 1 less power. So x to the n, when differentiated, becomes n x to the n minus 1. So for example, x squared becomes 2x to the 1, or just 2x. Constant multiples of functions, y equal to a constant multiplied by some other function u of x, have derivatives which is that same constant multiplied by the derivative of that function, du dx. Sums of functions, when you have y equal to a function u of x plus a function v of x, the derivative of y is the derivative of u plus the derivative of v. So we say the derivative of the sum is the sum of the derivatives. Let's try those out on a few examples. First up, we've got y equal to pi squared. Pi is just a constant, so the derivative of y with respect to x, when we have y equal to pi squared, is 0. The derivative of a constant is always 0. When y is equal to x to the 4, well, that's just a power of x, so dy dx is equal to, bring the power down to the front, x, and then lessen the power, or decrease the power, by 1. 4 minus 1 is 3. Next we have y equal to a constant, 5, times another function, x to the 5. So what we've got here is dy dx is the constant multiplied by the derivative of this function. Well, that's just like this one up here. X to the 5 becomes 5x to the 4. The 5 drops down the front, and the power is decreased by 1. So we have 25 x to the 4 for our derivative. Finally, with y equal to 3x plus 2, here we've got a sum of two functions, 3x and 2. So the derivative of y with respect to x is the derivative of 3x plus the derivative of 2. The derivative of the sum is the sum of the derivatives. And our derivative of 3x is the constant 3, x to the 1 minus 1, or x to the 0, well, that's just 1, so it's 3. 3 times 1 is 3. Plus the derivative of 2, derivative of a constant, is 0. We have our result that the derivative of 3x plus 2 is equal to 3. Throughout the unit so far, we've seen lots of functions that fall into the classification of polynomials. Things like linear functions, quadratics, cubics, fourth polynomials, and so on are all examples of what are generally referred to as polynomial functions, which fit into this form. They're made up of constants, plus constants multiplied by integer or positive integer powers of x, a1 x to the 1, a2 x to the 2, and so on as far as you like. AI are always constants, and the n's are always integers. In fact, they're positive integers. So these kinds of functions are actually very common, and in fact when you get into higher mathematics, they're even used to approximate more complicated nonlinear functions. So they're useful to know how to differentiate them, because they pop up all the time. And we can come up with a rule to differentiate any polynomial by combining the four rules we've just seen. And that's exactly what we've got in this example. We need to derive or figure out a general formula for the derivative of a polynomial function. So I've just rewritten the polynomial function there, just to refer to. So looking closely at the polynomial, we have that f of x is equal to, well, it looks like a sum of a number of terms. an x to the n, an minus 1 x to the n minus 1, and so on down to a1x and a0. Remember that one rule said the derivative of a sum is the sum of the derivatives. So this means if our function is y, then dy dx, the derivative of y with respect to x, is the derivative of the first term plus the derivative of the second term plus the derivative of all the intermediate terms plus the derivative of the second last term plus the derivative of the final or constant term. Notice I've popped in green there d dx. Now don't think of that as a fraction that you can cancel the d's. It doesn't work that way. This is kind of it's almost like a symbol that sticks together and means differentiate whatever's inside these brackets. So you can't treat this like a fraction. It means to do something. Differentiate the thing inside the brackets. Well, then we need to treat each of these little derivatives separately. And basically all of them are the derivative of a constant, the a, multiplied by a function of x. And whenever we have that, we know that the derivative is actually that constant pulled out, multiplied by the derivative of the function of x. So that gives us an times the derivative of x to the n, plus an minus 1, the derivative of x to the n minus 1, and so on, a1 derivative of x, and finally, we can just do this one straight away. It's the derivative of the constant a0. Well, we know that that's just 0. Next, we've got a whole bunch of derivatives of x to a power. And remember, the derivative of x to a power is found by pulling the power out the front as a multiplier and reducing the power by 1. So we end up with n outside of n multiplied by an x to the n minus 1, n minus 1 pulled out the front times an minus 1 x to the n minus 2, and so on all the way down to a1 times x to the 1 minus 1, which is x to the 0, and that's just 1. So a1 times 1 is just a1. So there we have our general formula for the derivative of a general polynomial function. We can use that anytime we like, but it's better not to remember the rule. It's better just to remember the way that it's found, pulling those constants out and then differentiating the different powers of x and adding up the results. Well, it turns out even though that rule was derived just for polynomials with positive integer powers of x, the same idea actually works regardless of whether those powers are positive integers or not. So we can actually use the same ideas to figure out these examples. Why don't you pause the video now and try these out yourself. When you come back, I'll quickly run through the solutions. Okay, so in the first one we have differentiate 1 gives us 0 plus the derivative of x to the minus 1/3. We pull the minus 1/3 out the front and then reduce by a further 1 the power to give minus 4 on 3. Then bring the 3 out the front to multiply by 4 gives 12, and reducing the power gives 2. So we have minus 1/3 x to the minus 4 on 3, take 12x squared. Similarly, we've just got powers of x here, pulling the powers out the front as multipliers gives us 90x to the 9 plus 10x to the minus 3. Assuming c is a constant, we've just got a derivative of 0 there. And we have our results. Finally, a few more rules that we can use for the nonlinear functions that we've talked about so far. Natural log, exponential, exponentials with some multipliers in them, tan, sine, and cos. Again, these rules can be derived in slightly more complicated ways using the definition of the derivative, but for us, we can just use the rules and apply them when we need to. So some examples. Note that this first one, log of 5x, isn't in the right form to use this rule, which is just for log x. But if you remember your log rules, the log of 5x is equal to the log of 5 plus the log of x. So we can say that dy dx in this case is equal to the derivative of log 5. Log 5 is just a constant, so it's 0, plus the derivative of log x, which is 1 on x, straight from the rules. Then we have y equal to 3e to the x. Well, this is just 3 multiplied by e to the x, so the derivative is going to be 3 multiplied by the derivative of e to the x. Our rules tell us that the derivative of e to the x is actually e to the x. Y equal to e to the 3x, then dy dx equals, looking back, we have e to a constant multiplied by x. We bring that constant out the front and write e to the same constant x. So we have 3 e to the 3x. Next, y equal to cos of 3x. Well, my rule tells me that cos of a multiple of x is minus that multiple sine of the multiple x. So we have minus 3 sine of 3x. With sine it works differently. The minus doesn't pop up, but we still pull the 5 out the front to give us 25. Sine becomes cos, and the same argument, 5x. Finally, with tan x, it's a funny looking rule, which brings in a new function that we haven't really talked about, the sec function. So tan of a multiple of x is that multiple times sec squared ax. So we have 2 times sec squared 2x. So there's some derivatives, figuring them out from rules and also from definitions. Have a go at some of the examples in the worksheet. There's quite a few of them. And if you need to, try to find some more either on the internet or maybe in some reference texts from the library before you move on to the next slide, where we're actually going to start using derivatives.